What if we were charged with the task of modeling this function mathematically? So we see that this function is periodic and that it's a step function. So that it comes up, over, down, over, up, over, right? And so we see that it is in fact periodic. Okay, so we might hypothesize that we could use sinusoidal functions to model this function. Because let's take a look at some sinusoidal function. Here is the sine function and the cosine function. And we see that these are periodic functions, so maybe we can use these to mathematically model this. And we would be right in making that assumption. So Joseph Fourier, in the early 1800s, hypothesized just that and then proved it. So let's take a look at what he proposed and then later proved. So he proposed that this function could be approximated by some constant plus a sum of cosine and sine functions, a combination of cosine and sine functions, and that any function could be modeled with this, given that you could find the coefficients, this a sub n and this b sub n, to match it up, right? To make things fit, okay? And also this constant here, a sub 0. Okay, so we look at these, and let's look at this sine function, let's look at this cosine function. Which one of these do we think is going to do a better job of modeling this function? Which one do you think will do a better job? Well, I would guess that the sinusoidal function would do a better job, the sine function that is, because it approximately matches the period. Well, it exactly matches the period. Look, this one has come from negative pi. At negative pi, it's coming down and over. At negative pi, this is coming down and over. And then from 0, this is 0 to pi, it's coming up and over. And then this is coming up and over. So if we superimpose this on top of this, it would do like this. So this sine function is a better approximation to this than this cosine function is. The cosine is off, right? It's out of phase with the function that we're trying to model. So if we were using these terms here in our mathematical model that we're used to model this, these cosine terms would be working against us. So we conclude the following. When we use, for modeling odd functions, let's use the sine terms, the sine function. And for modeling even functions, let's use the cosine function. Make sense? Now there will be some functions, remember I said any function. So there'll be some functions where you will use a combination of cosine and sine terms. But for this one, because it's strictly an odd function, you will only use the sine terms to model this function. And in the next tutorial, in part 2 of this series, we will show that that's true. Okay, here we go. So let's take a look. The hard part, the brilliance of Joseph Fourier was identifying what these constants would be. And here they are. So, Joseph Fourier in the early 1800s said, what if we let the period be equal to 2L? Then these things would be true. Okay? So, the proof is in your book. We're going to do an application and zip through this kind of quickly. But the application, I've done this, I've been in your place, I've learned this before. And the application is where you really see it come together when you graph it. And you see how what will happen when you graph it is the function will come up. You'll watch it on your calculator. It'll come up and it'll do this number. And then when it gets to here, it'll zip down like this. And I'll do this, like that. So, and the more terms you add, if you added an infinite amount of terms, then it would match this thing exactly. But of course, no one can add an infinite amount of terms because infinity is not a reachable thing, but we can add a lot. And so these squiggly lines the humps will get smaller and smaller and smaller until it looks like you can't see it with the naked eye. You have to zoom down, with your with your zoom function on your calculator, you have to zoom down really tight to see the wiggling, right? The squiggling lines. Okay, so you see that this for A0, it goes from negative L to L. They're all integrating from negative L to L. So half the period, right? Half the period to the positive of the other period. But notice, of the same period, it's all one period. Notice something, that this thing goes from negative L to L, so that's one wavelength, isn't it? That's one period, right? Because this one goes, the period, it goes from negative pi. One cycle is this is one cycle. Boom, 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 boom. That's one cycle, right? Negative pi to pi. So what's the total period? It moves over by pi, and then pi again, so the period is 2 pi. So the period is equal to 2 pi. And so solving for L is equal to pi. So we would integrate from negative pi to pi, and then this f of x here is the function itself that you're trying to model. But notice that this function, we can't just integrate, it's not a continuous function, it's a step function, so we can't integrate continuously from here to here, so we have to break it up into pieces. So I'm going to write f of x, I'm going to write a0 right here. Step out the way here. a0 will be equal to 1 over L is equal to pi, 1 over 2 pi. Yeah, 2 times L is pi. Okay, times, open bracket, the integral from negative pi to pi, and we're going to, well no, pardon me, we're going to go from negative pi to 0. We're going to break it up. And then f of x, from here to here, f of x is equal to what? Negative c. So we put f of x in here. This is negative c dx plus from 0 to pi, and then from 0 to pi, look, the function is c. From 0 to pi, it's positive c. Okay? And if we do this, we will see that a0 is equal to 0. Right? Because look at it. You have this area here, which is the negative area, and you have the same area, which is positive, so they cancel. And a0 is going to be 0 for this example. But this is just to show you that how we're going to break this up. And we're going to do this trick here. We're going to do this trick for a sub n and b sub n. And a sub n will have an a1, a2, a3, a4. And for b, we'll have b1, b2, b3, b4. But question, what do you think all the a's are going to be equal to? 0. Why? Because this is not helping us. This is not a good model. This guy is the one that's matching up closest. This guy is working against us. And Joseph Fourier developed a model, or a mathematical construct, that was very clever and self-correcting, if you will, because all of these terms come out to be 0, and we'll show that in the next tutorial. I'm going to step aside and give you a clear screenshot. Part 2 is coming.